Welcome to the 68th Theoretical Physics Colloquium by Dr. Matteo Buzzegoli of Iowa State University. He received his PhD from the University of Lorentz in 2019. During his PhD studies, he also spent a year as an exchange PhD student at Stony Brook University. After finishing PhD, he had a postdoctoral position at the Florence University and the Italian National Institute of Nuclear Physics for 2 years, from 2019 to 2021. And since this year, he is a postdoc at Iowa State University. His research interests include relativistic heavy ion physics, relativistic statistical mechanics, chiral matter, matter with vorticity, and many other things. And today he will be talking about anomalous spin rotation coupling at finite temperature. With that, I'll give the microphone to Matteo.
Okay, hi everybody. Thank you, Igor, for the nice introduction and for the invitation. And thanks to all of you which are here. So, so today I will speak about the possibility that spin rotation is anomalous in a medium at thermodynamic equilibrium. So first of all, I will tell you what I mean by spin rotation coupling, what experimental evidence we have for it, and how this is related to the Einstein equivalence principle. And some of these topics were already discussed by Oleg in this same colloquium series a couple of weeks ago. So I recommend you also to watch the recording of this presentation if you haven't already done that. Then I will discuss how the premises of Einstein equivalence principle do not hold in a medium for a quantum field theory at finite temperature, and how this allows the spin rotation coupling to be anomalous. And lastly, I will show how this anomalous spin rotation coupling is connected to the radiative corrections to the axial vortical effect. So to understand the spin rotation coupling, it is useful to make the analogy with the magnetic moment. So we know that a charged particle with spin s, it is associated with a magnetic moment given by this formula, and where Gb is the magnetic moment G factor. And so from now on, I will refer to the G factor as simply as a magnetic moment. And so we can detect the presence of this magnetic moment, for instance, in an atom. If we include, if we turn on a magnetic field, then the Hamiltonian of the system will change by this coupling between the magnetic moment and the magnetic field. And this can be revealed by the Zeeman splitting of the energy levels of the atom. Or we can look for the precession of the magnetic moment around the magnetic field, which precedes with the frequency given by the Larmor frequency. So analogous to this coupling, if we have a system which is rotating, for instance, if you are in a non-inertial frame, you are observing it by rotating, then we expect a coupling between the spin of the particle and the rotation of the system. And J omega, because of this analogy, is called the gravitomagnetic moment, J omega. For instance, we can see that we must include this term. For instance, if we consider the Dirac equation, and we write the Dirac equation in a non-inertial frame. So what we have to do is we have to replace the derivative in the Dirac equation with the covariant derivative. And inside gamma, we have to introduce the spin connection, which is built with the tetrad vectors. And for if you observe write the Dirac equation for an observer with velocity u, acceleration a, and rotation omega. And you can construct this tetrad, and then you can write the Dirac equation, and you find that indeed the associated Hamiltonian of the system contains this coupling between the rotation of the observer and the total angular momentum of the system. So these contain the spin and the coupling between rotation and spin. So we say that the Dirac equation predicts that the gravitomagnetic moment, the G factor, must be equals to 1. So this should be also be true for any spin, and not only for the non-inertial frame, but also for the system with actual gravity, where the metric tensor contains rotation.
Matteo?
Yeah.
There is a question from Chin Yang Wang. Why is it called gravitomagnetic moment?
Yeah, because as we can define the magnetic moment, it is related between this coupling within magnetic field and this magnetic moment. We can, because there is an analogy between the say the Chiral force and the Lorentz force, or even more so between the generalized Einstein equation and Maxwell equation. Then they can translate the magnetic field with the gravitomagnetic field, which is the rotation inside the metric. And so we have similar coupling. So this is called gravitomagnetic moment.
Isn't it the same as spin orbit?
Spin orbit, yeah, spin orbit depends on how it arises. Usually it's coupled with the orbital angular momentum. They use a spin orbit to define in atoms because usually is obtained because you write now the magnetic field in point of view of the particle. This then include the then you find the coupling with the magnetic field and the orbital angular momentum. But this is arising because all you are observing the system from a non-inertial frame, which is, so the omega is the rotation of this non-inertial frame. And or if you have gravity with some with the metric at the component of time space different from zero, you can associate a gravitomagnetic field and have this coupling. But essentially, it is similar to spin orbit coupling. Sometimes you can also mix them. Sometimes you can mix the two. Using Zeeman splitting, we know we can also have some direct evidence for the presence of this coupling. This was done, for instance, was explained in this paper, where they studied the ground states of these two mercury isotopes in two different experimental settings. One in which they turn on the magnetic field along the rotation of the Earth, and the other where the magnetic field is in the opposite direction of the rotation of the Earth. And since this is experimental, the lamps and the Earth, you are in a magnetic frame, so based on the argument I told you before, now you expect also this coupling in the interaction of the Hamiltonian. In this experiment, they were looking for a different kind of spin and gravity coupling, but the data was later interpreted by Mushroom in terms of this spin rotation coupling. And experimentally, they can measure the ratio of this, the energy difference because of this splitting between the two isotopes. And if you take the difference of this ratio into the two with a magnetic field parallel and anti-parallel to the rotation of the Earth, you obtain that this should be equal to this expression, where all the magnetic moments are are known because we can make other experiments to derive them. And the only unknown is the gravitomagnetic moment G omega. So the data agrees with the gravitomagnetic moment different from 1 and close to 1. So G omega equals 1, as predicted by the Dirac equation. You can also make a more precise analysis of these data. You can find this in this paper. If you allow the gravitomagnetic moment of the two isotopes to be different, you find these inequalities. So again, the gravitomagnetic moment is consistent with the value of 1. Also, more direct manifestation of this spin rotation coupling can be found in the Barnett effect, which is the magnetization of the ferromagnet induced by mechanical rotation. And this can be explained with spin rotation coupling, because if you start spinning your ferromagnet, then you will have an energy difference given by the product of the rotation and the angular momentum of the system. And this must be compensated by the coupling of the magnetic moment and the effective magnetic field. So since the magnetic moment is proportional to the total angular momentum of the field, you can deduce that the magnetic field is just omega divided by the Chiral magnetic factor, gamma. So yes?
There is another question.
Yes, this is a very short question here. The spin, is the intrinsic part of the freedom, and they couple to orbital angular momentum, whether it's rotation, that's very natural. But in your coupling, I noticed that you also have this rotation and orbital angular momentum. Are they the same thing? I mean, if a particle is rotating, is the same thing? Is the angular momentum?
The rotation is not given by the particle. It's not the particle which has a rotation.
Well, it's part of the. I mean, what if your frame is rotating, all the if you think about the fluid is rotating like vorticity. Are they the same thing? The orbital angular momentum. I mean, when you rotate, when the frame is rotating or the fluid is rotating, is that the similar thing, like that has some kind of orbital angular momentum?
It's just a matter of definition of how to call things. Of course, you have a separation between the microscope, if you consider the vorticity of the fluid, that is a macroscopic vorticity in a sense. And for instance, for fluid, I'll show you how this rotation spin coupling appears in a few slides. So I think that will answer your question. The next slide, I will talk about also this possibility. Where rotation will be interpreted as the vorticity of the fluid.
Yeah, well, okay. Maybe we can decide later, because your audio it makes very hard to understand you. But that's I'm a little bit concerned. I mean, confused by the rotation versus the orbital angular momentum here.
No, the rotation here is a microscopic quantity.
But now you in this case you have the coupling. I mean, then that's what I don't understand. Where is coupling come? It's the same thing. It's not like spin orbital angular momentum. They're coupled. That's it. Anyway,
you can see this as a non-inertial effect. So if you're observing, what I was trying to tell you with this question is that if you observe your system and you are rotating, you have this coupling between the rotation of your observer and the spin. Is this clear?
Anyway, for me, it's still not very clear what's the difference between rotating and orbital angular momentum.
Maybe it's possible to add that omega, this is a rotation of the medium, which is a particular case of vorticity, and orbital momentum is orbital momentum of a particle, right? And
yeah, but the particle is part of the medium, right?
No, this is considered particle in the medium, in the rotating frame, like in the textbook. So if frame is rotating, then it's extra term in the Hamiltonian. And what Matteo stressed, that the relative coefficient between orbital momentum of particle and spin of particle is 1, which is just precisely the equivalence principle. So orbital momentum of one particle, and collective rotation of medium. Is it? This is just from another side, maybe.
I mean, in principle, you can derive actually. You can derive from spin orbital coupling to the spin rotating coupling, because that's, and you can actually derive that by using spin orbital coupling, and then you calculate the orbital angular momentum of a rotating system. Then you can derive this. So I don't know how to divide macroscopically between rotating and angular momentum.
Careful. I mean, in gauge theories, the separation between them isn't even gauge invariant. What gauge symmetry is the fact that you can exchange angular momentum for a longitudinal component of spin of a photon.
It seems like this is going into the discussion now.
Yeah, we probably should come back
to return to this at the end of the talk.
Yeah.
So let's. Was saying, that this Barnett effect, you can explain by this spin rotation coupling, and so you obtained it by this analysis. You indeed obtain the magnetization of the ferromagnet that we can observe. Similarly, now you have kind of the opposite effect, is the Einstein-Diaz effect, that you have on a ferromagnet in a stance which allows for rotation, and you magnetize the ferromagnet, then it will start spinning. Macroscopic, here again, a macroscopic spin, macroscopic rotation. So you can also explain this in this way. Then you can also then look for a direct measurement of the spin rotation coupling in the area collisions, because especially during peripheral collisions, the nuclear matter created after the collision is generated with very high angular momentum. Here again, the angular momentum here is a macroscopic of the full, the total angular momentum of the system. And because of the spin rotation coupling, then you expect that the particles emitted by the nuclear matter the spin are perfectly aligned along the total angular momentum of the system, so they should have a global polarization. This can then also interpreted using the statistical mechanics, because the system is you can consider the system at a local thermodynamic equilibrium, and then you have the spin degrees of freedom of the particles are equilibrated. Then you expect this global polarization. But even in this case, you have to introduce this spin rotation coupling, because for simplicity, consider the global equilibrium, global thermodynamic equilibrium. So we want to give, if you want to write now the statistical operator of the system, which has a vanishing angular momentum, then you have to include this term. This is just not the coupling between the angular momentum and rotation. And this type of equilibrium has been started by Landau for a non-relativistic system, and later by Wienkin for a relativistic system. But to have a more manifestly covariant expression of the statistical operator, one can use the Zubred's method of non-equilibrium statistical operator. And you can add the statistical operator of equilibrium of the system with vorticity in this way, where here you have the coupling of the angular and boost momentum operators coupled with the vorticity. So here the A is the acceleration of the fluid, U is the velocity of the fluid, and omega is rotation. Then these terms coupled to J recreates the coupling between rotation and the angular momentum of the system. And so this kind of operator was used, especially in applied to Rayleigh collisions, to obtain the mean spin vector of Dirac particles. And you see that using this statistical operator, because of this coupling, you expect that the polarization vector is directed along the vorticity of the system. And this formula has been used in different models, and it proves to be able to predict the value for polarization in Rayleigh collisions. So this is a direct measurements of the direct manifestation of this spin rotation coupling. And here it is possible because these the quark-gluon plasma created in Rayleigh collision turns out to have a very high vorticity, so it's allowed the detection of this effect. So now I'll show you why we expect this type of coupling and what the evidence we have for it. And I've made the analogy with the magnetic moment. And we know that the magnetic moment, the Dirac equation predicts a value of the magnetic moment G factor is equal to 1, but we know that this is renormalized by interactions. So the magnetic moment is anomalous. And you can relate the magnetic moment to the form factor of the matrix element of electric current. So we can ask if it is possible that also the gravitomagnetic moment to be anomalous. It turns out that the gravitomagnetic moment is protected by the Einstein equivalence principle. So you cannot have anomalous gravitomagnetic moment, but the gravitomagnetic moment should be equal to 1. So to give you a better idea of this, give you two arguments. One is a postulate from the equivalence principle, and then one is a low energy theorem from quantum field theory. So for the equivalence principle, you say that if you want to describe the motion of the particle in gravity in an inertial frame, you can also describe this motion in the absence of gravity, but from in a non-inertial frame with acceleration. You can think to use the Lorentz theorem to do a similar approach to describe the motion of a charged particle in the presence of the magnetic field. And you can say you can describe this motion in the absence of a magnetic field by using a non-inertial frame, which has a larger frequency given by this formula. So you can think to, because of the analogy between the Lorentz force and Coriolis force, and so it's probably the analogy which is known as gravitomagnetism, because the Einstein field equations are formally equivalent to the Maxwell equations when they are linearized. And so you can postulate that the motion of a particle with a gravity field which has this component different from zero, you can describe the same motion in the absence of gravity, but in an inertial frame which rotates with a Larmor frequency. And if we explore the analogy, we realize that this Larmor frequency has the same form of the electrodynamics Larmor frequency, but we have to replace to the electric charge a gravity charge, which is just 2 times the mass, and the magnetic field with a gravitomagnetic field defined in this way. And this implies that we already know the gravitomagnetic moment of the particle. This will be given by the same formula as the magnetic field, and we have to replace the electric charge with the gravity charge. So this implies that the gravitomagnetic moment should be equal to 1.
Matteo, quick question regarding the changing from the inertial frame with the magnetic field to a rotating frame. What about the electric field? When you go from one to the other, you will also get the electric field because of the boost. So there is no equivalence. And also, what about the spectrum in quantum mechanics? The spectrum is quantized in the present magnetic field. What happens with all of this?
Yeah, of course. So for the electric field, you can also include an acceleration. I think it's possible to read the effect of an electric field with acceleration. But for the magnetic field, of course, I'm not saying that the magnetic field can be started with the equivalence principle, because you have to prove the quantum effects in these changes. But if we extend on the equivalence principle for rotation, we can exploit this analogy and realize that if indeed we cannot distinguish between the effect of an inertial frame and rotation, then we have this kind of coupling, and the gravitomagnetic moment is equal to 1. So the message is that for magnetic field, electromagnetic field, of course, you have to include quantum effect, but if you really apply equivalence principle, the effect of gravity, then you cannot affect the way the spin of a particle couples with the rotation. Yeah, maybe it's more clear if we see these as a low energy theory in quantum field theory. In this case, you have the coupling with the gravity is given by the Lorentz variant term, which couples the stress, the energy momentum tensor with H, which is just the tensor, which it is the deviation of the metric with a flat space-time. And then you can compute the matrix elements of stress energy tensor at low momentum transfer. And because of the conservation equation of energy momentum tensor, then the form factors of stress energy momentum tensor can only be given by the value of these conserved quantities that are the total momentum and the angular momentum of the system. In particular, these second form factors is related to with the gravitomagnetic moment. So what they say is this is true for any interaction, so you cannot renormalize the gravitomagnetic moment. Especially this is true in general, but for the Dirac field in particular, it was has been studied first by Donoghue and Donoghue, and they show that the matrix element of the stress energy tensor for the Dirac field can be written in this way, and these two form factors, when evaluated at zero momentum transfer, no matter what interaction you are including, this must be equals to 1, and this implies a gravitomagnetic moment equals to 1, so no anomalous gravitomagnetic moment is possible. so you can see that because of the Einstein equivalence principle, the possibility of anomalous magnetic moment is forbidden. But what happens when we consider a particle in a medium at thermal equilibrium? So in this case, we have a preferred reference system because we have a thermal bath, we have a medium. And so what means we can always make measurements and compare them to the thermal bath. So in a sense, because we have this special reference system, we can distinguish between the effects of acceleration and the effect of gravity. And so this means that the presence of the medium of thermal bath make the Lorentz invariance of the vacuum and the Lorentz invariance of the theory. So essentially the premises of Einstein equivalence principle, which states that you cannot distinguish between gravity in a non-inertial system, breaks down. So it seems that it's possible in this setting to break the effects of Einstein equivalence principle, and it was indeed shown by Donoghue, Holstein, and Robinett that the inertial mass and the gravitational mass of the fermion, for instance, in quantum electrodynamics, they differ. And they differ because of the temperature effects.
Sorry, can I ask a small question? How are these masses defined, inertial and gravitational?
Yeah, okay, no, this slide.
Okay.
Yeah, so yeah, I want to explain this. So consider quantum electrodynamic at finite temperature. So we can define different masses for the Dirac fermion. Phase-space mass, which is obtained from the pole of the propagator. Then you can obtain an inertial mass, which is how the particle and the acceleration of the particle is related to the force exerted to the particle, so how much it responds to an external force. And then you can also define a gravitational mass, which is how much the particle interacts with the gravitational potential.
Sorry, Matteo. So this means that equality of inertial and phase space is gauge dependent.
Is gauge dependent? Why? We say the acceleration with force is not gauge dependent until the end.
Because here you assume that some particular just that. Or can this be considered as again? This is gauge dependent. You need that vector potential is zero, right? Or
yeah. So what I've shown here. Let's start with the inertial mass. You can put any force you want and try to define the inertial mass. As a simple case, now here you can consider what happened to your particle if you have a constant electric field, which arguably is the most simple case. You have a constant force, and so to see how the inertial mass changes with the interactions and for the presence of the medium, you can study the Dirac equation, and you renormalize all the quantities, and so you choose you have this coupling because of gauge invariance, and you choose anyone such that to relate an electric field, the constant electric field. But it's just a choice, it's a setting. Of course, you can say, let's try if this is true for any force that I can think of, but I haven't checked this. This is just one example. And so if you take this Dirac equation, make the non-relativistic limit, then you can obtain the Hamiltonian of your system, normalized with interactions and with the presence of the medium. Then you can obtain the acceleration of your particle, and you see this is given. It is given by the ratio of the force, so the electric force, because I make this choice, and it is divided by the phase space mass. So this is that a inertial mass is equal to the phase space mass, and phase mass is obtained by the pole of the propagator. I won't go to the details, but it's important to mention because of the presence of the thermal bath. Is the Lorentz variance breaks. You have to consider also the thermal effects. So sigma here is the self-energy of the particle, which affect the propagator S. And if you evaluate the pole from this of the propagator, you can obtain the phase space mass, and you obtain that all zero temperature effect, and included here in this M, but then you have also contribution from temperature given by these quantities for the quantum electrodynamics. So here what we find that essentially the presence of a thermal bath increase the inertial mass. And this makes sense if you think of your particle, which is moving in the medium. So if you try to pull it with the force, the particle will interact with the medium, and this will essentially this is a sort of viscosity. So you expect that this will resist the pull, and so you expect that the inertial mass will increase. Then we have to compare with the gravitational mass if it is also affected by temperature. And to do this, we use scattering theory. So we have the coupling with gravity is given by this coupling between energy momentum tensor and the h, the deviation from metric. And then you can obtain your scattering amplitude by this quantity, where you have to consider the Fourier transform of the tensor h and the matrix elements of the stress energy tensor. And to obtain coupling with the gravitational potential, you choose a metric for gravity, which is obtained from an homogeneous distribution of mass. So you have this quantity where phi is the gravitational potential. So if you normalize the energy momentum tensor, and you can obtain the amplitude. And if you compare this amplitude from what you obtain from the potential given by the gravitational potential, you comparing the two, you obtain the gravitational mass of your particle. So what we have to do is to normalize these matrix elements. This was done by Donoghue, Holstein, and Robinett for quantum electrodynamics, and they consider at first group they have to consider these diagrams. And for this type of coupling with the gravitational potential, you just need to evaluate these diagrams at zero momentum transfer. So for Q equals 0 or the same P prime equals to P, and define that the matrix elements are given by this expression, where you see that again the presence of the thermal bath brings the Lorentz invariance of the theory. And then, so from this you can obtain the gravitational mass. If you make the ratio of the inertial and gravitational mass, you see this is not 1, so they are different. And the difference is given by this quantity for temperature lower than the mass of the particle. So this calculation shows that indeed at finite temperature, the inertial mass and gravitational mass are different, so there is a explicit breaking of the weak Einstein equivalence principle. Extending the argument, we can also expect that because of this breaking, also the gravitomagnetic moment could be anomalous. And to understand what might happen, why, let's consider one of these diagrams, which renormalize the stress energy tensor. which we can call the photon polarization. So you have the photon clouds surrounding the fermions interact with the stress, the energy momentum tensor, or the graviton, if you like. And if you are at zero temperature, what told us that essentially the virtual photons emitted by the fermion are rigidly rotating with the fermion, and overall you don't find any effect on the way the Dirac fermion couples with in the medium, the rotation of the medium. Instead, if you are in a medium, not always you have the photon from emitted by the fermion, but you also have a photon coming from the medium. And a medium which is rotating means that these have some sort of polarization reacted along the rotation. So because of the presence of the thermal bath, you have these thermal photon which mixes with the usual photons emitted by Dirac fermions, and these overall could give a modification to the gravitomagnetic moment. So this is just the intuition. So we have tried to make the calculation, again using scattering theory. So the scattering amplitude is the same, but this time we have to use a different metric because we have to use a metric with rotation. So you can choose a metric coming from a non-inertial observer with rotation along the zeta axis. And we just need the first order in omega. Then we can evaluate this amplitude, and then we can compare it to the amplitude which is obtained from the spin, from the potential given by the spin rotation coupling, which is given by this expression, where C is the two-component spin out of the Dirac field, and sigma are the Pauli matrices. So comparing the two amplitudes, we can obtain the gravitomagnetic moment of the Dirac particle. In this case, it turns out that we cannot stop at zero momentum transfer, but we have to go to the first order. And so we have, in general, we can write the form factors of the energy momentum tensor at first order in momentum transfer. And because we are not at zero temperature, we have the fluid velocity u, and we can also define other vector. So we have additional form factors appearing in the matrix elements compared to the zero temperature quantum field theory. And so from this scattering amplitude, what we realized that only these four types of form factor can contribute to the gravitomagnetic moment. And if we make the comparison, eventually we find that the gravitomagnetic moment is given by this combination of form factors. And then it's by taking the limit of zero momentum transfer and taking the spatial part of the total momentum going to zero. So we can obtain these form factors again by renormalizing the energy momentum tensor from quantum electrodynamics. So I told you this time we have to go to the first order in momentum transfer, and we obtain that indeed the gravitomagnetic moment could be anomalous, and these modifications are given by these quantities. So we explicitly show here that the effect of temperature and coupling affect the gravitomagnetic moment and breaks again the Einstein equivalence principle. To explain it in an intuitive term, I have discussed this diagram, but if you look at the actual contribution, we see that at low temperature, overall this diagram does not contribute to the anomalous gravitomagnetic moment, but it affects it at a high temperature. We have also this condition for this value to be valid, because we are essentially using one particle states to define the matrix elements. So we cannot push the temperature too high, because we have to define one particle states, and so we have to be in a weak interaction regime. So let's look on how large you can expect this correction to be. So we have already this for quantum electrodynamics. Let's consider an electron. So essentially the difference of the relation between inertial and gravitational mass and this anomalous gravitomagnetic moment are essentially the same order of magnitude, given by the square of the Kaplan constant and the square of the temperature divided by the mass square. So if we consider room temperature, this is of order of 10 to the minus 17. So it's a very small correction, and so it's not possible currently to use, for instance, a electrostatic experiment to see if the inertial mass, gravitational mass are different, because currently the maximum precision is 10 to the minus 15, and then also we will have to design the experiment to look for this particular effect. But if we can push this correction to its limits, so we can consider a temperature of 1.5 MeV, and in this case, the anomalous gravitomagnetic moment becomes relevant. So,
Matteo, can I just ask very quickly, is there a spin dependence as well as a mass dependence or not?
No.
I mean, here you did fermions, but if you were to do, spin 1, spin 1, 3, half, spin 2, etc., for hadrons, would there be a spin dependence?
For Einstein equivalence principle, we don't expect that the gravitomagnetic moment should be equals to 1 for any spin. If you can try to perform this analysis for another particle, and in the case, I don't know if it would be different. Yes, it is possible, of course. Also, it depends also this particular value, of course, also depends because we should choose the derivatives for the quantum electrodynamics. So more general definition could be given in terms of these form factors. And if these are spin dependent, then you can also find spin dependent there. But I don't know for sure. Makes sense not to look for systems where there is a high vorticity and high temperature. So we can make an order of magnitude estimate for the anomalous gravitomagnetic moment of quark S inside the quark gluon plasma. So if we consider here we have considered quantum electrodynamics, and we want to consider quantum chromodynamics, we just have to include this factor in front. And so we can estimate for the using the constituent mass of the quark S, a value of an anomalous gravitomagnetic moment of these values. So with this very rough estimate, we can expect quite a larger contribution to the gravitomagnetic moment. Maybe it is possible to detect the presence of this anomalous gravitomagnetic moment by looking at polarization measurements. Maybe it is possible to reveal the presence of this anomalous gravitomagnetic moment by looking at the energy dependence of polarization. because if you use a simple combination model, we see that the polarization of lambda particles is essentially given by, essentially inherited completely by the polarization of quarks. And so if pushing this to the limit, if we can expect that this anomalous gravitomagnetic moment translate directly to the polarization, so we expect deviation from polarization of this organ. So we expect the polarization to decrease more at high energy because temperature will be higher. But of course, this is just a seed of an idea, so because these are simplistic arguments must be analyzed better. More steps in this direction is if we can connect the anomalous gravitomagnetic moment with some kind of observable, and can directly connect the anomalous gravitomagnetic moment to the axial vortical effect, especially to the radiative correction of axial vortical effect. So the axial vortical effect is one of many quantum effects in relativistic fluids. It is a non-dissipative effect, and essentially it is the mean axial current induced by the rotation of the fluid. And what you see here is its value for a free massless Dirac field. And this can be explained for massless Dirac fermions exactly from spin rotation coupling. Because if you have a fluid with rotation omega, then from spin rotation we expect that the spin of the particle were aligned preferably on the rotation of the system. But then the right-handed particles will have their momentum aligned along the spin, and so they will move along the direction of rotation, while the left-handed particles have the momentum aligned in the opposite direction. And overall, you expect a net flux of axial current along the rotation of the fluid. So this can be again described using statistical mechanics with the statistical operator of the fluid with vorticity. And in this way, you can understand the possibility of this effect, because if you include the rotation, then you inside your statistical operator, then you take the symmetry of your statistical operator, and in particular rotation brings rotation and parity symmetry. And so this allows the axial current, the mean axial current, to be directed along the rotation. And so actually, if you can make the calculation, so this is just one way to see the axial vortical effect, but if you can take the axial current of a Dirac particle and compute its mean value with the previous operator, and you can use, for instance, linear response theory rotation, and indeed obtain the axial vortical effect. And WA is the axial vortical effect conductivity that for the massive free Dirac fields given by this expression, which reduce simply to this quantity for massless field. But more generally, if you include the rotation, you can give the axial vortical effect conductivity in terms of a Kubo formula. They will be given by some correlations between the J, the angular momentum of the system, and the axial current. In imaginary time formalism, you can write this correlation in this way, with this integral, and there is the correlation between the stress energy tensor and the axial current. And this correlator is done with the homogeneous thermodynamic equilibrium, so without rotation. So you can use standard techniques to evaluate this quantity. Notice here that we must use the Beninfante stress energy tensor because we want to reconstruct the total angular momentum of the system. Based on this Kubo formula, we can also write these in terms of Feynman diagrams. So if we have interactions, you can use perturbation theory, and then you have your three-level diagram for free theory, and then additional diagrams given by interaction. Of course, this first diagram will give the result of free theory that I showed you before. Otherwise, we have to include other correction. Similar to this Kubo formula, there is the formula, the Kubo formula for the Chiral vortical effect, which is the electric current induced along the rotation of the fluid. And we have just replaced the axial current with the vector current. In this case, you need the breaking of charge and of parity. So usually this occurs when you have an electric imbalance and a chiral imbalance, which is not required for the axial vortical effect. But the two Kubo formulas are formally equivalent. So you can study by the diagrams, studying the diagrams if radiative correction are possible. This was studied in these two papers. So what we find for the vector current, for instance, for the electric current, which is conserved, if you study gamma, these diagrams, which contributes to this Kubo formula, then you can write what the event is, and then you conclude that only the three-level diagram, only the free theory can contribute to the chiral vortical effect conductivity. So there are no relative corrections to the chiral vortical effect. But if you consider the axial vortical effect, so the axial current induces a long rotation, the axial vortical effect is no longer conserved, so you cannot use the same argument. And so if you consider massless field, you have to include the chiral anomaly. So in this paper, they show that we can extend this argument if you first split the diagrams in two types. One, a fermionic type, where the energy momentum tensor is inserted, is connected through fermion lines, and a gauge type diagrams, which is connected with gauge fields. And you realize that these type of diagrams are not connected to the chiral anomaly. So for this type of diagram, it acts as the axial current is conserved, so you can use previous argument and show that this does not give relative corrections. Instead, the gauge type diagrams are connected to the axial vortical effect that can be shown that this kind of diagrams indeed can give relative corrections. If you consider instead the massive field, you also have this additional term which contributes to the divergence of axial current, which is proportional to the mass and to the pseudo-scalar. And in this case, also fermionic type diagrams can contribute to relative corrections. For massless fields, so first order in quantum electrodynamics, so we have to include these diagram to evaluate the axial vortical effect conductivity, and it was evaluated and give these relative correction. And so you see here that on the left, essentially you have the same diagrams for the polarization diagram, which contributes to the anomalous gravitomagnetic moment. So we can expect that the anomalous gravitomagnetic moment can have roles in this relative correction. So what we have analyzed is the relative corrections of the axial vortical effect for a massive field. So we have to consider this Kubo formula And so we can think of the interactions as they are acting only to change the ways of the fermion interacts with the rotation of the medium. And so we can try to isolate this effect. For instance, if we go to, so we can perform this analysis if we go to the large mass limit. So we can think of this internal fermion line as one particle state. So if we can separate this large mass limit, if we can separate between energy scale, so if we can separate from short distance interactions, which normalize the energy momentum tensor and the axial current, and can separate between low energy contributions, which are instead given by thermal averages. And formally, we can do this by replacing the energy momentum tensor and the axial current quantum operator with their sum on multi-particle states. So this can always be done. So we have, for instance, the energy momentum tensor will be given by this sum and integrals of creation and destruction operator, and are given by the matrix elements of the energy momentum tensor. And similarly for the axial current. So we can replace this expression inside this Kubo formula, and then the thermal averages are obtained with standard techniques by evaluating thermal averages of the creation and destruction operators. So if we replace this expression, we perform the large mass limit. We obtain that the axial vertical effect is obtained by this expression. Right, you have this integral over the derivative of this trace, and this trace is given by this expression and is related to the matrix element of the stress energy tensor. So we can simply evaluate these matrix elements, and you can normalize these in the same way as we have done for the gravitomagnetic moment. And even in this case, if we perform this trace, we see that if you consider all the form factors, it will eventually replace the gravitomagnetic moment. So if you plug here all the possible form factors and evaluate the trace, you obtain the gravitomagnetic moment. So essentially the axial vertical effect conductivity is proportional to this gravitomagnetic moment. So we can place this trace inside here and make the integration and simplify a little, and we obtain this expression where G omega is the gravitomagnetic moment because it is given exactly by the same combination of factors that I showed you before. So here we see clearly the connection between the axial vertical effect conductivity and the gravitomagnetic moment. In particular, you see that if you replace value of 1 to the gravitomagnetic moment, you obtain the axial vertical effect conductivity for the free field. Instead, as we shown, if there is an anomalous gravitomagnetic moment, then this will result in a relative correction to the axial vertical effect. So can evaluate the first loop correction for the massive field, and by replacing the previous values of the anomalous gravitomagnetic moment, we obtain this expression. So in summary, what I've shown you that because of the breaking of Einstein equivalence principle at finite temperature, the gravitomagnetic moment of a particle can be anomalous, and we can relate these to various effects related to spin rotation coupling. I will show you explicitly that the relative correction, the axial vertical effect are connected to this anomalous gravitomagnetic moment, And possibly, if we look at the hadron collisions where vorticity very high, temperature is high, it may be possible to reveal the presence of an anomalous gravitomagnetic moment. This concludes my talk. Thank you for the attention.
Thank you very much for your presentation. Now we will have some time for questions. So if you have questions, please raise the hand. Okay, Oleg Chiral, go ahead.
Thanks, Matteo, for interesting and clarifying talk. And I have a comment and that maybe technical question. And the comment is just concerning the definition. Should what you observe, and what you observe is the modification, the coefficient of spin, right? In Hamiltonian, spin rotation coupling. Just my point is that orbital rotation coupling in Hamiltonian is also changing, right? Because of Lorentz force. And its coefficient is just the coefficient of gravitational mass. And in this sense, two coefficients of L and S change. So
I'm not sure about that, if the coupling with the orbital momentum should be connected with the gravitational mass.
Right, exactly. So
no,
this is
like
sure.
I don't see that. Maybe you know that, but I haven't checked.
No. I think this is because of Lorentz force. It should be because it's forward matrix element of energy momentum tensor. Well, what I mean that in principle, if you have L and S with two different coefficients, you may express it, re-express it as a sum of L plus S and difference of L plus S. And the sum of L plus S comes with sum of with average of coefficient and L minus S with difference. What I mean that equivalence principle means that also another formulation that orbital angular momentum, classical rotator, and spin rotates with the same precession frequency. So the sum L plus S preserve this notion of equivalence principle. The difference of L minus S clearly violates this. So I fully understand that your definition is clear, and also in the corrections to AVE, just G of spin enters and its derivative. From the other side, if you consider some, I would say, just physical interpretation as equal precession of spin and orbital, here the difference of spin and inertial mass should enter, and it's of the same just magnitude, but of different sign. Maybe some physical interpretation can be found for that. And I have a technical question just concerning this, your summary slide. The coefficients in two very different limits of small temperature and large temperature are very close, right? So it's 1.6 and 5 to 36. Is there any reason for such closeness? Because if you somehow now put some interpolate by smooth function, it will be just very flat. So
the reason there is a big meaning in this is just because at low temperature, these are all approximation. So low temperature, because in these are obtained by these diagrams at finite temperature. So these are obtained by integrating also the Fermi-Dirac and the Bose-Einstein distribution coming from the propagator of fermion and photons in the diagrams. And at low temperature, what happens is that the Fermi-Dirac distribution, because the fermion has a mass, so it is limited, reduces to essentially to the Maxwell distribution, and this is suppressed exponentially by the ratio d over m. And if you include these in this term here, you will result also in a logarithmic term on P over N. But if you instead the boson distribution function is for massless photons, and this gives the integration, the leading contribution to this term are of the T square over M square. But if you do the opposite limit of large temperature, boson contribution remains the same, but fermionic contribution, in this case you can neglect the mass, so they also give rise to the same T square over M square contribution of the integration. But in the mean, so then is a matter of numerical factors which combines together. And in the middle you should find logarithmic terms and other terms which then will smooth out in some say non-trivial way.
I see. Okay, thanks for.
Okay, next question, Giorgio Torriere.
Hi, thank you for a really interesting talk. Just as a sort of comment, and I find that talking about the violation of the equivalence principle at finite temperature a little bit misleading, in the sense that it's like you said, I mean, for the reason you said, if you have finite temperature, you have a preferred frame. And this goes at the heart of the ergodic. If you have the ergodic hypothesis, you have a time, you have a definition of time, and then you have a preferred frame. And then you have a preferred frame. So it's not a locally Lorentz invariant. I mean, the issue that happens is that your manifold stops being locally Lorentz invariant, but starts being in local equilibrium somehow. And then, however, what this is interesting about it is that there is a formal mathematical analogy between a thermal state and an accelerated frame, and the Unruh effect. And that's a consequence of the real equivalence principle. And that's a consequence of the real equivalence principle. I mean, there is actually a big amount of literature talking about whether quantum field theory is not general quantum field theory is generally covariant in this sense, because you have some tree-level calculations where what is interpreted in the inertial frame as interactions with the semi-classical field, in the co-moving frame, it's interpreted as interactions with the thermal bath, but the matrix elements for given processes are actually invariant. The matrix elements for given processes are actually invariant. These calculations are really limited. They are essentially in the probe limit. You have a particle being in a classical trajectory pulled by a string. There are no fluctuations. There is nothing else. But these things actually seem to work for quite a few interactions, for quite a few gauge theories. Now my question is, if you have these anomalous interactions, if you have these anomalous gravitomagnetic interactions, is it possible to, that way, one could break the real equivalence principle in the sense that the interaction with the semi-classical field in the inertial frame and the interaction with it, which makes the particle accelerate, and the interactions with the thermal bath and the co-moving frame will not transform covariantly. The matrix elements will not transform covariantly into each other. My immediate comment is probably not, because every single matrix element that you have has this inverse dependence on mass. So it goes away. For an effective theory built around local equilibrium, you have sort of the probe limit. So the particle being accelerated is immune to any fluctuation. So it's infinitely massive. And it seems that your effect also goes away in the infinitely mass limit. Is that the case? Sorry for the somewhat long-winded question, but yeah.
That's important to make this clarification that, as I said, it's true that saying that is a breaking of Einstein equivalence principle must be misleading, because it's not that we have to throw away Einstein equivalence principle, but we just the same thing with breaks, Lorentz invariance, which is the result of it. So I don't know if you want to call it breaking or Einstein equivalence principle or another way. And also that, yes, this calculation is valid in the non-relativistic limit. You have to define one particle states, and this is not obviously obvious, but you have to measure this. You have to go to the rest frame of the particle. So this is limited to these hypotheses. And so,
but be careful, because there is a formal analogy between acceleration and temperature.
Yeah, but for rotation is more difficult because there is no analogous of Moore effect for rotation. So it depends how you define your rotating vacuum state. You can have similar effect or not. So it's less obvious connection between. There is not an analogous of a precise analogous of Moore effect for rotation. So it is not easy to answer with a definitive statement.
That's true.
Okay. Then the next question is Karl Waldsteiner.
Hi, yeah, thanks for this very interesting talk.
Hi.
Yeah, I have, let me see, my first question concerns, so you considered the contributions of the thermal bath to the coupling of the fermion spin, right, to the graviton, so to speak.
Yes.
Yeah, but when you have, and you considered, say, a QED plasma.
Yes.
Right, but if you would rotate such a plasma, rotation would also couple to the photons, right?
Yes.
So, and especially in applications to the quark-gluon plasma, I mean, the plasma is really, quarks and gluons. So the gluons would also couple to the rotation. So how one can apply this, because it's not clear to me how, the amount of rotation will be distributed between the angular momentum spin and then between the gluons and the fermions.
Yeah, so the overall rotation of the system, of course, it takes into account all of these of the particle in the medium. Then when you consider an interaction, of course, to see how the spin of the fermion couples with the rotation. First look, we consider this diagram. So the parts of the photons in the medium are included by these interactions here.
But the external lines of fermions here, right?
External lines, exactly. So
there should be diagrams for the external lines.
Yeah. So the question is, if you want to know how the polarization of the photons interacts with the rotation of the medium, you have to extend this argument for the photons. And so instead of considering the energy, the matrix elements are related to the Dirac equation, to the Dirac field, you have to consider the equations for the photon and matrix elements for the photons, and see how this is affected.
Yeah.
So
no, I'm worried about how could you access these effects experimentally, right? Because all the coupling you can do is somehow rotation, or in this picture with a metric, right? And the metric couples universally. I mean, it would couple in the same way to the fermions and to the photons, and you assume the photons to be important for the quantum dynamics of the whole system because you take the quantum effects into account. So probably I misunderstood, but at the moment I don't see how you could experimentally access this particular coupling.
Yeah. So again, here omega, the confusion omega here is sort of a macroscopic rotation.
Right.
Unfortunately, there is always not the problem.
Sorry, can you lower the level again of the microphone? Now the audio is very.
I see. Why it rises by itself?
I can rise my volume and you.
Oh, okay.
Yeah, it's better now.
Yeah, I was saying it is. There is always not a problem. If you want to describe these omega or macroscopic omega in terms of microscopic terms, of course, this is very difficult. Like, in a sense, it's just like asking how you quantize gravity. How you describe the gravity in terms of quantum field theory, and so this would be difficult. But if you are perfectly fine with staying with the linearized gravity, and you have definition of rotation in this way, or for instance, you want to describe a fluid, and you describe vorticity as a sort of Lagrange multiplier, in the sense that these are well defined object, and so you can think, for instance, for the polarization. For instance, you can give an effective description of a coupling between the spin of the fermion and the thermal vorticity, include this anomalous gravitomagnetic moment, and see how the polarization is affected. But of course, there is all the difficulties, because of course the calculation, this result is for weak interaction, first order, for large mass and everything. So maybe it's not straightforward to say what the result could be. But in principle, you can see it from polarization. If you were able to detect an axial vortical effect in the area in collisions by again looking at the separation of charge or something, it is in principle possible to say, okay, we need an anomalous coupling between spin and rotation to account for this observation. Of course, I don't have an analysis an observer which will resolve the problem, but in principle, I don't see any problem.
Okay, thanks.
Okay.
I'm not sure, so
you have more questions, right?
It seems, by the way, it seems your computer is adjusting the level automatically, because it started out well, I could understand very well, and then as you kept talking, it went back to.
Sorry, it's my computer, which I don't know why automatically rise my.
It's your settings in the Zoom, but it's a bit too late to change.
Okay. Okay, and then can I make one, or probably I'll leave it.
Go ahead.
Not just one, because you said this thing that the chiral vortical effect for the vector current will not get renormalized. Right. So yeah, can you go back? There's the formula for the chiral vortical effect in the previous slide. I think 2 slides before.
You mean this one?
No, I mean before, like 30 or 29 or 30. And then it was even earlier, 30. Yeah, here it is. You see, here the question is, you see, you consider the theory where the gauge fields are dynamical, have a important quantum dynamics, right, on the right-hand side of the axial anomaly equation, right? But in this case, the axial current is actually not the conserved current anymore, right? Because its divergence is proportional to a quantum operator, and so it would have quantum fluctuations, etc. contrary to the case when the right-hand side of the anomaly equation is just a classical field, right? Then there's no quantum dynamics there, and whatever you adjust it to, the d mu j mu follows just this classical anomaly. But if the right-hand side is an anomaly equation itself, then it's not anymore conserved current.
Yeah, I think we are looking at a different slides.
No, I'm actually what I want to get at in this situation. In this situation, when the axial current isn't really a conserved current, it's not clear what is the axial chemical potential mu a.
Yeah.
Right.
Yeah.
So the statement that this doesn't get renormalized is not completely clear to me, because I don't even know what is meant by mu a in that case. Or if you switch on a mass, right? If you switch on a mass, you can induce some initial state with a chiral imbalance, but the mass will certainly destroy chirality in the time evolution. And so there is it's not clear what mu a means in this situation. To me, what mu a in this formula means.
Yeah, no, that is true. You cannot define this axial chemical potential because you don't have conserved quantity. So
for the axial magnetic effect, the situation is a bit better because you can get away.
Yeah, you can.
You have p squared and mu squared, and these are good conserved quantities. So in this sense, the AME is actually in some sense more clearer, theoretically more stable than the other guy.
Yeah.
Just as a comment.
Yeah, because the axial current doesn't, the axial vortical effect doesn't require an axial imbalance.
Yeah, exactly.
That's what I'm trying to convey in this slide. So if your system is rotating, is providing the right pseudo tensor, so the axial vector and the rotation has the same properties under parity, dimensional, and so on. So this is easier to define.
Yeah.
But if you make so for the axial vertical effect, if you want to study if there are relative corrections, you can see from the grammatic proof that you can indeed expect some relative correction because the axial current is not conserved, and so certain type of diagrams can indeed contribute, and also these are supported now by the actual calculation, which show the presence of relative corrections.
Okay.
Okay.
Any other questions? Any other questions before we wrap it up?
Well, if possible, I have a naive question, maybe not only to Matteo, but to other present experts. Isn't it possible to write down the Dirac equation in thermal medium? If so, then it can be possible to go beyond the linear approximation for gravity. For dense medium, probably it's possible just by introducing chemical potential. What about thermal medium? Did anybody try ever to do that?
Well, I'm not quite sure what you exactly mean, but the self-energy, for example, of the Dirac field is changing. So in a way, this is kind of what Matteo was using.
Yeah. But maybe, so is it possible, just the question is it possible to write down the Dirac equation in the thermal medium? And then it's a way, if to put the covariant derivative, and it's well-defined way, and we did it for arbitrary gravitational fields. Then it's possible, so if it is possible to do in thermal or dense medium, then it's maybe possible to do also for arbitrary gravity, for which corresponds, I don't know, to fast rotation and whatever.
Well, but the temperature is not just like a kinematic modification of the equation. That's the thing. it kind of brings all the fields up and all the interactions. So there is nothing exact for sure. It's just, I believe it's just the fact that how you include thermal effects, not that you are writing in a thermal background. It's not a background in a sense, I think.
Maybe at least for some approximation. Well, anyway.
By the way, even chemical potential, by the way, you mentioned that even the chemical potential, when you just add the chemical potential, that doesn't mean you're describing the dense media with the bare parameters, because in fact, dense media changes the properties. It introduces from the surface and everything.
Well, I see that it is not obvious, but maybe. Okay.
I don't know.
Yes, yeah, okay, thanks.
Matteo, if you want to add something before we wrap this up.
No, I agree. You can write a generating function, with including temperature, chemical potential, and everything. So you can use, for instance, path integral and everything. To, but it is something you have. So this is like a sort of an effective theory of writing in action with some parameters. And, I don't know if this is your aim to do that.
Okay.
Any other questions? If there are no questions, I would like to use this moment to thank Matteo for a nice presentation. And with that, we will end the official part.